Let's define a power series. And a power series is an infinite polynomial in this form. It's an infinite series, which is, as it turns out, an infinite polynomial that is written in this form. So it is the series from n equals 0 to infinity of c sub n. We call these c sub n's right here, we call those the coefficients. Let me grab my highlighter. We call those the coefficients. So c sub n's are the coefficients of the series. And we write out the series c naught plus c1 times x to the first plus c2 times x squared plus c3 times x cubed. Now, this is the series that we say is centered at x equals 0. This polynomial that we're looking at, we're focused in at x equals 0 because x to the nth technically could be written as x minus 0 to the nth power. So we know that this is going to be focused in at x equals 0. We're looking at that infinite polynomial, but focused at x equals 0. It is centered at x equals 0. Another way to think of that is if you just zoom in on the x-axis, we're thinking about a polynomial, and we're centering it, we're building it right around 0. We're centered at 0 in this case. Now, the more general way to write a power series is to say that it is x minus a. So we are centered at x equals a versus at 0, or a can just be equal to 0. This is the more generic and the more general form. So again, the c sub n's are the coefficients, and notice here we would be just building a polynomial as we write this out with coefficients c naught, c1, c2, c3, and so on and so forth, x minus a to the first power, x minus a squared, and building the powers as we continue to add more and more terms in this infinite series. So this guy is centered at this generic value a. Now, of course, a could be 0, and we would just go back to the previous definition that I have right there. So more generally, we use the second definition I've given here, where we've let a be any value, and it can be equal to 0, and then that would just simplify to the version we have above. All right, so a power series is just a series where we have x raised to some power for each fixed value of x. So for specific values of x, whatever number we're plugging in for x, this series just becomes a series of constants, right? If we plugged in x equals 1 or x equals 2 or x equals pi, whatever value we plug in for x, then this series just becomes an infinite series that we could test for convergence or divergence. And therefore, what we're thinking about, and I want to highlight this part down here, this is actually a function because we plugged in x, and the domain of this function is all the values for x for which the series would converge. And that's what we're going to work with on this video, is talking about how do we find those x values? How do we figure out what values of x would make these series converge? And that depends, of course, on the coefficients and where we're centered and all of those things. But that's the general definition of a power series. And let's look at one just to play around with it and see what it looks like in practice. Okay, so to start off, I'm going to look at this example. So this is the series from n equals 0 to infinity of x to the nth. And again, remember that a power series is an actual function, right? We've added into our series, we've added in a variable, making our series that we're looking at now, these power series, actual functions. And so here, this is a very simple one, just x to the n. So what would that look like? From n equals 0 to infinity, this would become the infinite polynomial. They are functions that are infinite polynomials. When we plug in 0, we get 1, and then when we plug in 1, we get x, and then we get x squared, x cubed, x to the fourth, and so on. This is infinite, so this goes on and on and on. So again, remember, these are polynomials. They are infinite polynomials, these power series, but it is a polynomial. And why do we want to think about infinite polynomials? Well, we are going to get to a place where we can connect these to functions that are not polynomials, and we're going to think about how it might be easier to work with a polynomial than a function. And if there's operations we need to do, integration we want to do, applications we want to do on a function that we're not able to do mathematically with the tools we have so far, if we could represent that function as an infinite polynomial, polynomials are really easy to work with mathematically. And they can be graphed, they can be integrated, differentiated. You know, there's all sorts of things that we can do with polynomials. Polynomials are easy functions to work with. So if we can represent other functions as a polynomial, an infinite polynomial, that opens the door to being able to do all kinds of things with functions that we maybe were limited to doing before. Okay, so back to the one that we're looking at. This particular one that we're looking at, if I want to think about, okay, so for what values of x does this series actually converge? Because this is a function, right? This is some function, but what is the domain of this function? What values, and that's the question, what values of x will this series converge? That's going to be the domain of our power series. And so this particular one that we're looking at is actually a geometric series. Look at this. Each time we go up, we're multiplying by x. And so this is it's a geometric series where the common ratio r is actually equal to x. And we know that geometric series we get convergence when the common ratio is less than 1. So when we're thinking about this power series will converge because it is a geometric series. It will converge for the absolute value of r, which is the absolute value of x, is less than 1. So this is going to converge when the absolute value of x is less than 1. Not only that, we also know what it converges to. Remember, just a quick review on geometric series. Geometric series will converge when r is less than 1 to a over 1 minus r, where a is the first term and r is the common ratio. So little recall right there on geometric series. So if we've just identified this guy, this power series, as a geometric series with a common ratio of x, we know it will converge when the absolute value of x is less than 1. And not only that, we know what it will converge to. It will converge to, well, what is A? A, in this case, is the first. Remember, A is the first term when we talk about geometric series. And so A is 1, and the common ratio we already talked about, R, is x. And so this is going to converge to 1 over 1 minus x. That's the function that this is actually converging to when x in absolute value is less than 1. So we can actually say that the geometric series from n equals 0 to infinity of x to the n, which again was 1 plus x squared, that infinite polynomial, is equal to 1 over 1 minus x, that function. When, now we do have to be specific here. This is true, right? This equality right here, this is true, but not for all x's. This is only true when the absolute value of x is less than 1. So what that means is that we can look at the function, and I grabbed this image over here because I want to go over to DESMOS here in just a second. I grabbed this image. This is where we're going to head over to in DESMOS. What this means is that we could look at the function 1 over 1 minus x, and then we could look at this infinite polynomial. And what we'll do is we'll build that polynomial in DESMOS. We'll continue to add terms until we get, we can actually go up to 50 on the little applet I have. We'll go up to 50. We'll add the first 50 terms in this infinite polynomial, and we will see how that polynomial actually is converging right to this function 1 over 1 minus x, as long as we're looking at it just for the absolute value of x less than 1. So before we do that, though, I just wanted to mention that back to our power series, this power series was centered at, this was like an x minus 0 to the nth power. So this power series was centered at x equals 0. So if we think about where this convergence is happening, if we zoom in at 0 on the x-axis, this power series is going to represent this function as long as the absolute value of x is less than 1. So that means that we can go from 0, where we're centered at, that means that we can go to the right 1 unit and we can go to the left 1 unit because the absolute value of x is less than 1. So we can go over to positive 1 and to the left to negative 1. And this is what we call the interval on which we can converge, the interval of convergence. So since we're centered at x equals 0 and we got convergence on the interval from -1 to 1. So if we just zoom in, now of course if we are not within that, if we are out here beyond 1 on either direction, if we are beyond 1 on either direction in magnitude from 0, then we will get divergence. We don't want to look at this polynomial and this function being equal to each other outside of this interval of convergence. They will not converge outside of this interval of convergence, but on that interval of convergence, within that radius, what we think of as the radius from that center point, within that radius from 0, we will get nice convergence. And so let's look at that in DESMOS. Okay, so here we are in DESMOS, same graph I had on the notepad, but here we are in DESMOS. Here is the function y equals 1 over 1 minus x, and you can see that that is graphed in this sort of purple color graph. You can see that has that asymptote at x equals 1 right there. And you can see here we are, if we center at 0, so keep your eye on what happens from -1 to 1. If we look at where we are, centered at 0, and we think about this infinite polynomial, let's start to build that infinite polynomial. And this is, we're going to let this upper value on this series, on this summation, we're going to let that grow. Right now we're just at 0. So if we're right at 0, the first term here, just the constant term, when we're thinking about that polynomial, it's just 1 times x to the 0. So that's 1. So you're seeing right there, you're seeing the graph of the infinite polynomial that we're going to start to build here. You're seeing that right here, that is just that value. Oh yeah, let's zoom over there. Let's zoom in a little bit more. I think, we don't really need, I wanted you to see that second part of the function 1 over 1 minus x around the asymptote, but we're really focused from -1 to 1. So let's zoom in right there. So here is that constant term 1, and now let's go. If we add another term, so we take 1 and then we add another term. So we increase this now, this n, we're going to go from n equals 0 to 1. So we have 1 plus x, and you can see that linear term right there. Obviously, better approximation of the function than just the constant term, but not that great yet. Let's go to 2. So if we go to 2, and now you can start to see we're starting to build a function, a polynomial, that between -1 and 1 is getting closer. Obviously not that great of an approximation yet, but it's getting closer. And then when we go to 3, now you can start to see we are getting the red polynomial that we're adding more and more terms into that polynomial, and we're watching that go up. And now let's go, I'm going to go ahead and just play it out, and so you can watch it grow, get closer and closer approximation. And on the right side right there, I'll just stop it right there. On the right side, I only am going up to 3 right here. If I zoom out a little bit, well, we're going to go out on the x-axis. Let's change this too. Okay, so we're just zooming in and in and in, and let's go. And you can see we're just getting closer and closer. I'm going to stop it right at 50. There's the first 50 terms in that infinite polynomial. And you can see right here, you could see that little tail right there getting closer and closer and closer. It was just approximating closer and closer and closer. If I zoomed out, you would see the same thing happening over here as we approach 1, where that asymptote is. But obviously that's growing without bound right there because of the asymptote. But you can see that infinite polynomial that we're looking at is converging to this actual function, which we showed mathematically on the notepad. We showed that this series right here, this infinite series, converged when the absolute value of x was less than 1. And because it was a geometric series, we knew what it converged to. It converged to this actual function right here. And so this function can be approximated by this infinite polynomial, and it will be exactly this infinite polynomial as long as we're looking at it on that, what we call interval of convergence, where it converges. And so here we are back on the notepad, and we can see right here, that's that connection that we've just made, that this infinite polynomial is equal to this function when the absolute value of x is less than 1. Or another way to say that, as we did down below, when x is on the interval from -1 to 1. Now, I used some terminology when I was going through this example. I was saying things like radius and interval of convergence, where we are converging. And so let's define those here at the end of this video. Okay, so when we look at a power series has 3 possibilities when we talk about its convergence. Its convergence when we talk about the power series, its convergence could be that the radius of convergence is equal to 0. So when we look at this power series and we determine where it converges, it could be that the radius of convergence equals 0. This is very limited convergence. If the radius of convergence equals 0, that means when we graph it, we are literally only going to only converge for x equals a. And so it's literally like just a single dot. It doesn't have a radius, right? Its radius is equal to 0. So if the radius of convergence, the area on which it converges, is 0, well, then we just say that it converges only at x equals a. Now, the other possibility, these are the two extremes. The other possibility is that the radius of convergence, where it converges, is actually equal to infinity. Now, if that occurs, if we're centered at x equals a and the radius is infinity, what that means is that we can go infinitely to the right of where we're centered and infinitely to the left of where we're centered. And if we can go infinitely to the left or to the right, what that means is that we converge everywhere. We converge everywhere. And if we converge everywhere, what we say is that the interval on which we are converging is from negative infinity to infinity. So that's the corresponding interval for which x converges, for the values of x which converge. Above, I didn't highlight this one, but I'll come back and highlight this. When the radius is 0, we don't actually have an interval. We only have one point at which we converge. And so we just say that we converge at x equals a, or on the set x equals a. Okay, so those are the two extremes. The other possibility is that we have some positive number r on which the series converge. We define that r to be what we've been saying so far, the radius of convergence. And we say that if we are centered at x equals a, and we can go r in either direction and still have convergence, so we can go to the right r, we can go to the left r, what that creates is it creates an interval of convergence from a minus r to a plus r. Now, here's the deal. When we look at this, it could be that we converge at these endpoints or that we diverge at these endpoints. So that's the piece. I'm going to go ahead and make a little star right here. We will have to test the endpoints individually for convergence. It could be the case that we converge at those endpoints or diverge at those endpoints. I just deleted my little squiggle. It could converge at those endpoints. The series could converge at those endpoints, or it might diverge at those endpoints. It could converge at both of them, converge at just one of them. That is why, notice here that we actually have 3 or 4 possibilities for the interval of convergence. The interval of convergence will either include the endpoints or not include them, depending on if we have convergence of the series at those points. So that you just have to test for, and you have those 4 possibilities. So again, let's go back to that original example, this example that we were looking at. And as I was going through this example, I was sort of throwing around those terminologies to introduce them, but let's actually define them officially here. So this particular series, again, was centered at x equals 0. It had a radius of convergence of 1, and it had an interval of convergence of -1 to 1. And that we were able to get out of, and I used IOC to abbreviate, interval of convergence, and R for radius of convergence. We were able to get that by looking at that connection to the geometric series, and what we know from all of our work in the previous chapter on infinite series and geometric series. We knew that the geometric series would converge when the absolute value of that common ratio was less than 1. So we can see that right here. This is the case where the endpoints do not have convergence. If we think about plugging in -1 or +1 into the series, if we had -1 to the nth or +1 to the nth, neither one of those are going to converge. They both diverge. Therefore, we have the open interval, and that is, again, coming out of what's already been proven through the geometric series in this course. Okay, when we come back, we're going to look at all kinds of other power series and determining their radius and interval of convergence.